Or I was asked to talk about ocean a little bit. I didn't know what's the right pitch, so I hope I did the right pitch. I'll talk to you a little bit about the ocean, ocean dynamics, and how they come about to affect the climate, and that might be a good segue to what we'll hear next from Claire. So I started off as an atmospheric scientist, and then I became an oceanographer. There is a lot of similarities. There's a lot of differences. Not so many differences. There's a lot of differences in the lingo, and I had found it hard in the beginning, but now I think I'm totally into the lingo of oceanography. So excuse me if I'm using that lingo, and please point out when I do so then we can find like the common. It's just, sometimes it's just the word, and then the whole concept is the same. Okay. So this is how ocean surface currents look like. If you just go just below the sea, just below the waves, I think this is around 50 or 100 meters deep. This is from a simulation, what you're looking at here, the North Atlantic. It's a global simulation, but it's also, it's what we call a state estimate. So it has all the information from all observations at the time that the simulation was made into that. And as we simulate forward, we nudge the system to go towards the observations, to match the observations where we have observations. So it's as close to reality as possible. And you can see it's full of eddies. I trust you heard about mesoscale eddies in the atmosphere. In the ocean, they're a bit smaller, like 5 to 10 times smaller in the size. But other than that, they're similar. All right, so let's see what we're going to talk about. First of all, I just like this. It just makes you kind of bring things in perspective. Okay, it's like it's full of oceans. So that's one. I mean, it's also full of atmosphere. Usually, this comes into contrast to people that are more land-centered, like for example, Andy Pittman or something. But anyway. So, okay, why do we have a circulation in the first place? Generally, the sun heats it up, hits the ocean, hits the atmosphere, and then somehow this sets things in motion. Because if there was no circulation, then we would have the equator, boiling water, because the sun has been doing that for ages. And, it would be freezing at the top. Somehow this heat has to be transferred to the poles and then emitted back out to space. And if all we get in is emitted out, then we have a nice stable climate. If what we got in a little bit stays in, then we have some climate change. But that's what we're trying to understand, how heat it moves around in the Earth system, and how the ocean, the atmosphere, the land all together interact, exchange heat, energy, momentum, and whatnot, and then emit it back out. And that's when we are thinking about climate and trying to predict the climate, understand the climate, that's what we're trying to do. All right. And okay, why ocean? Like that's another motivation, a bit more not based on artistic or how the ocean, how the Earth looks from above, but this is a graph that's been in the IPCC report, the last IPCC report. So if we ask ourselves, from the excess heat that has been produced in the Earth system post-industrial revolution, where is this excess heat? Where is it? All right. We'll see that 90%, 80% is in the ocean. So you see, this bit is ocean, this bit is ocean, this bit is ocean. All right. So most of the excess heat, the ocean takes up and puts it in the abyss. And us, as earthling creatures living in the atmosphere, this is quite important for us, because otherwise we would have been experiencing not 1.5 degrees, but whatever, I don't want to say a number, but much more. Okay, so how the ocean circulation changes, or how the ocean circulation does that, or where this heat intake it happens. It's quite important because like a little bit of change in the ocean circulation, and if the ocean decides to take 5% less heat in because of some change in the circulation or whatnot, then we would be experiencing 15 instead of 10, which is quite a lot compared to what we're experiencing now. So that's why that's another motivation why we want to study the ocean. All right. So then I wanted to make some, like we could do this on the board, or we could do this here, so you can have the slides. So, well, I'd like to hear from you. We'll make some like differences or whatever about the ocean and the atmosphere. Like, all right, well, different densities, yes. Density, like 1 and like 1,000, say, more or less. All right, that comes into effect a little bit. But like from a fluid's perspective, whatever density, there's some other thing. I mean, I'll hear from you, and we can do. Yeah, just speed it up. Yeah. What? Different heat capacity. All right. Okay. What did you say? All right. Okay. So like heat capacity. Let's write it in general. It's like here, heat capacity. I'll make it better later. Heat capacity. So I think what you meant to that we can have phase transitions in the atmosphere. Yes, phase transitions. We don't have phase transitions in the ocean. Yes, all right. We have when we start like thinking phase transitions. Okay, yeah, all right. If we put ocean ice, let's do that. Sea ice. Then it has become more of a similarity. Phase transitions, water, vapor. We have rain essentially. Oh, my computer wants to be in the US. And then phase transition, ice, water. All right, what else?
Stratification, I guess the ocean increases the pressure and the depth, and the atmosphere does the opposite.
True. But they're both stratified in that sense, okay. Yeah. Depends also how you measure. Okay, so like this decrease. So in that sense, they are similar because they're both decreasing their density as you go up, right? Compressibility, that is a big one. Compressible, and this is incompressible to a very, very good approximation. I didn't hear.
Memory.
What?
Memory. Like ocean have longer memory.
All right, that's good. Yeah, it's a good one. Yes, it comes into effect with, or let's call it memory. It's a good word. Memory. So what is like for the atmosphere? 7 days. What we would say? Typical like week. Let's say a week. So what? So for the ocean, it may be months. Okay, 3-4 months. Yeah. Like this is how I'm thinking about it is the typical lifetime that an eddy, a storm, lives. That in the atmosphere go for a week. A mesoscale eddy in the ocean will live for 3-4 months. Yeah, what else?
Like the time scale with predictability then, like atmosphere.
Yes, all right. I'll leave it there. It's kind of like the same or very connected. Yes. There's a couple of ones that come to mind, especially that. Yeah, that. They are both turbulent. But unless if you meant something else which you didn't express, like, because definitely they both have turbulence. Different turbulence though, sometimes, but like what, did you have some?
Components here
atmosphere different kind of temperatures? Well, yeah, well, that's a good one. So, and I'll put it up with the density. So, it's not that, yeah, the density, the base density is different, but also this is, you know, what, like the equation of state, EOS, depends on temperature and salinity, while that's not the case for the atmosphere, all right? Is it like that? That's a good, perhaps they also depend on depth, perhaps on other things, but I think the main difference is the salinity, okay? We need to, you know, carry around how much salt is there in the ocean. There's a salt plays a lot overall, yes?
Radiative properties, like if you're heating or cooling the atmosphere. So the ocean might be more reflective to radiation.
Yes, yep. All right, I'll put it in the middle because it's radiative properties, yes, they're different. All right, that's a pretty good list. There's a few things that I didn't think about, like in the morning. There's like one else, kind of, just a little bit, I mean, when I say it, they will say, oh, yeah, well, I didn't think about it. Yeah, all right, go.
Different depths, I don't know how much topography affect each of them.
Well, I think the topography is a little bit more, isn't? I was thinking of the topography. It's like the ocean has boundaries, like lateral boundaries, where the atmosphere doesn't. All right. So, coast, let's say coast, or lateral boundaries. Yes, they also have different depths, but you know that's like if you think about it, like in the more abstract fluid dynamics way. They don't. But that I mean, having lateral boundaries makes modeling much harder for the ocean. We cannot use spectral codes, for example. You know, we don't. While in the atmosphere, everything is like goes around the globe. Very nice. Okay. Don't know. Anybody can think of something else? These are quite a good list. All right. All right. So, all right. Let's see. Let's see what else. Okay. Now, I'll make this cleaner when I upload these things. All right. So, about the ocean, I want to talk to you about two aspects of the ocean circulation. One is what I will call lateral circulation, like you can think about it as being the horizontal circulation. It's not always horizontal everywhere, and I'll explain. We'll see examples. In the oceanographic lingo, we call this isopycnal, so that circulation that moves along surfaces of constant density, or isopycnals. How would you call it in the atmosphere? I'm sure there's something else like it. It's not, or you call it isopycnal. I have a hint of how you would call it in the atmosphere from this morning's chat, but you don't. Do you? By the way, out of curiosity, like in their everyday life, how many of you are more like waking up and thinking of ocean problems just to get in a vibe? Okay, I see 3. How many of you are like more into the atmospheric, like All right, and then there was some people who didn't vote. Like it's like land, biology. What are the other themes? Just to get the vibe, like so who am I talking to? What are other people doing? Land. All right, yeah, and that sums it all, or is there something else? I don't know, biology? No? All right. Okay, so in the atmosphere, do you call this isopycnals? I think you don't, because I remember that was one of my struggles. They're like, I don't know, is it the isotropes or something? Is it the same thing? Yeah, I don't see like a full commitment here. But anyway, so we'll talk about the bits of the ocean circulation that goes along isopycnals or along surfaces of constant density, and some bits of the ocean circulation that crosses them. Okay, So the ocean circulation like varies at many, many, many different scales and many, many different time scales. You see here a glimpse of that because what the movie shows is surface currents from one of the biggest global ocean simulations ever run. This is a simulation with a horizontal resolution of 1 to 2 kilometers. This is very, very high resolution for the ocean. Or if you think about it in terms of degrees, it's 1/48th of the degree. This simulation includes sea ice, which you don't see here, but it also has tides. These are what you're seeing here. All this is like twice a day, so you get an idea also of the time scale of the simulation. It's not many days. It's like the whole video is like 10 days or 12 days. That's why you don't see much else moving. But you see there's like big currents. There is eddies, all these circular features, which they almost seem that they don't move because the simulation is only for a couple of weeks, and then these eddies move at the time scales of few months. You see tides. You see waves, like moving around. These are internal waves, Rossby waves, near inertial waves at the surface. And there's also other things that we don't see. There's like turbulence at the time scales of meters that varies at time scales of minutes. This is usually at the top boundary layer of the ocean. I'll show you a movie a bit later. So there is eddies, mesoscale eddies, or sub-mesoscale eddies as we call them. The distinction of these two is a little bit vague, but usually when we say eddies, we are talking about motions that are in geostrophic balance, more or less, while when we say sub-mesoscale eddies, we're talking of motions that are not in geostrophic balance, and so the Rossby number is like much greater than 1 there. Then there is currents, and there is also the overturning circulation, which we cannot see, which is like a circulation I'll show you a schematic later. Perhaps have you talked about the overturning circulation in the atmosphere, like a Hadley cell or things like that? Yeah, so it's the same thing, but in the ocean. So from the bottom of the ocean up to the top and again to the bottom. So that circulation is really, really slow. That definitely happens, and it crosses some surfaces of constant density. But you can see different bits of the circulation are either isopycnal or generally moving along surfaces of constant density, or diapycnal, or both. Here, for example, for the eddies, I put both because if they are sub-mesoscale eddies, as I mentioned, eddies that are not in geostrophic balance, then they have a strong diapycnal component. So this is, as I said, there is also turbulence at the top layer of the ocean, which the boundary layer or the mixed layer, as we call it. And that turbulence comes in really, really small scales. And here I will show you a simulation of how that turbulence might look. So this is like a very, very, very small bit of the ocean. That's only 500 meters, 500 meters, 500 meters, and the top 200 meters of the ocean. And what you see here is temperature. And you can imagine that the atmosphere at the top is cold. Okay, imagine there's like cooling at the top. So while you will, if we let this run, you will see something very similar to Rayleigh-Bernard convection. So warm plumes from the bottom should rise up, and cold plumes from the top will move down. Okay. So let's see how that happens. It's a little bit of a mess, but that's how it happens. And as we let this go, you see these are, if you've seen pictures of convection, this is like the top, a bit of classical, convection rolls. If you see them from above, how they look. And as we let this thing go, you see that this layer that starts shallow becomes bigger and bigger. At some point, it will equilibrate. But this is what we call the top mixed layer. And in this case, this mixed layer is 100 meters now. But if we let it go, it might become more. So this top layer is very mixed because the turbulence is very vigorous there. So it has whatever the temperature is at the top, it's the same as the bottom, and that's what we call the mixed layer of the ocean or the boundary layer of the ocean. All this is like very, very fine details for climate models to capture. This is not, to the best scenario possible, this wouldn't be not even a grid cell in this big simulation that I was showing you before. So here, this is, and every grid cell is 2 kilometers, while here, this box alone is 250 meters, and then you see all this detail that it includes. So somehow, when we are trying to understand the ocean, same goes for the atmosphere, we need to be able to understand how turbulence at this scale, or motions at these scales of meters, interact with eddies of hundreds of meters or like of kilometers and hundreds of kilometers, currents that go around, from Queensland down to the Victorian border, for example, these type of scales, and then currents and the overturning circulation that goes all around, it spans the whole Atlantic basin or the whole Pacific basin. And sometimes, and these things are really interconnected, like one affects the other. You cannot really understand one if you forget everything else. For example, turbulence like that or motions like that what I'm showing you here, play a very big role in the shape of the overturning circulation, which has a length scale of 10,000 kilometers and varies over centuries. So somehow we have to understand everything together, unfortunately. So when I want to talk to okay, so let's hear, I'll break down a little bit this concept of moving along surfaces of constant density, or isopycnals as we call them, or across them. So say we have this scenario that the surface of constant density have this structure. So it's dense below, and it's light above, and they're slanted. They could be slanted. Of course, if you were in your bathtub, this wouldn't be like a state of equilibrium. But because the Earth rotates, and we have also Coriolis force, we could have a state in equilibrium that is like that, and we have some. I'll show you in a little bit. But say we had something like that, and we have a fluid parcel here, which has this density. If we move it up, then it becomes denser in an environment of a lighter fluid, so then it wants to go down. So it will go down. If we move it down, it's a lighter particle in an environment of a dense fluid, so it will want to move up. So that's like, this, if this happens, this will oscillate with the Brunt-Väisälä frequency or the stratification, as we call it. Same thing as we move it left or right, it will find itself being either denser in a light environment, and it will want to go down to find its density, its surface that it started with, or if we move it to the left, it will be a lighter parcel in a dense environment, and will want to go up. So doing this sort of motions, requires like paying extra energy, converting some of the potential energy of the system into kinetic energy. So it's a little bit costly. But if we want to move it like that, it's happy to move there without any restoring force to go somewhere else. So this is the motions that I was talking about, and I was calling them isopycnals, moving along surfaces of constant density. It's quite easy to do. So then we see a lot of vigorous circulation, ocean circulation, following these surfaces, because it's quite, you don't need to pay potential energy to do that. But to do this other, like, to cross isopycnals, it costs a little bit. So the ocean flow will do that at the not so often, okay, or much with more effort. So if we take a section of the ocean, this is a section in the Atlantic, and forget the big arrows for them now, but these thin lines are lines of constant density, of constant potential density. And you see they are slanted. They are very, very sloped here and here in the north, in the Arctic regions. Of course, this is an exaggeration because the depth of the ocean is only, I don't know, 4 or 5 kilometers, and this width is, 20,000 kilometers. So the aspect ratio is really, really, really small, but still the structure of the surfaces of constant density look like that. So in this schematic, you see this is what we call the overturning circulation for the ocean. For the ocean, it looks like that. There's two big cells. One cell is it goes like that. This is what we call the deep cell, and this is the, I don't even know if you call it narrow, shallow cell, I don't know, the top cell. And you see there's these cells cross surfaces of constant density. They have to cross surfaces of constant density somewhere. Otherwise, they wouldn't be able to close. So there are these motions here, for example, they're definitely diapycnal. They cost some energy to do it. This motion here is more closer to isopycnal because it follows a little bit the surface of constant density. So what happens here? We see there's motion moves, motions that move at the surface of the ocean or at the top layers of the ocean towards the North Atlantic. Then something happens here. We have heat losses because it's very colder. Heat losses or sea ice being formed. As soon as sea ice is formed, then the salt is ejected from the water because if you have some salty water and you freeze it, then the salt doesn't stay in the water. So we have what we call brine ejection. So then we have cold, very salty water there. And that's really dense, and then it wants to sink, and then it sinks. And somehow it starts moving the other way. Okay. Same here. We have here at the coast of Antarctica, we have sea ice formation, and here actually we have it's even colder. The water are the coldest waters we know. And then after sea ice is formed, they become also very salty. So then they sink to the abyss. And we have what we call here the dense water formation. And then people start calling, they start anthropomorphizing and giving identity to these water particles, which there's some credit to that, and it's helpful to do that a little bit, but you shouldn't overdo it. And they call this type of water that goes down Antarctic bottom water, or this other, this water that is involved in this intermediate cell here, the Antarctic intermediate water. We have the North Atlantic deep water formation here, and there's the whole zoology of namings for different waters that move around the ocean. You can follow, there's some, it's not just being anthropomorphizing, because the temperature and salinity of a water parcel here, because that's conserved, if you know what's the temperature and salinity of this water parcel here, then you can follow and see that it has more or less the same temperature and salinity properties. So that's what people are using to okay, we will identify the water that has this temperature and this salinity properties with, and call it somewhere, call it Navid, call it Antarctic bottom water, and then we can follow it around and try to understand the ocean circulation like that, because we know that there's water here that has particular TNS or temperature and salinity profiles. So if we find it also here, then we know that this must have originated from here, or there must be a connection somehow. Okay. All right. Now, like this dense water formation, I mean, this is a little bit of a schematic, and you expect that this happens everywhere, like for every longitude, because this is like just a slice. But it's very, very inhomogeneous and happens in particular, like this dense water formation that water forms and is dense and moves, cascades to the abyss. Doesn't happen continuous all the time or in every longitude around Antarctica. I'll show you here a video, and you'll get an idea of how that happens. Here, what we see here is the sea surface temperature, and this purple water is really, really cold, and it's where the sea ice will be formed, and then as soon as the sea ice will form, then it will become also really, really salty. So cold and salty means very dense, and it will want to sink. But we'll go into it and see how this sinking happens. It doesn't happen like all the same place, but it happens through, various canyons or various you'll see it's quite erratic and it's quite mesmerizing. So there's a video. The video talks now, but now I'm doing the talking. But anyway, we will go under the sea now and see how this dense water formation cascades down. So what's plotted here is a particular isopycnal that corresponds to the most denser water that we know. And you see near the Antarctic margins, it's at the surface, but somehow it cascades to the abyss. This is this is 2 kilometers deep or 4 kilometers deep. So that's how this thing happens. It's very inhomogeneous, very quite challenging to model. Not even mention to observe. To observe, it's like almost impossible, like to actually observe with measurements. But yeah, so then these are the type of, again, I'm just trying to give you a general overview. These are the other type of important processes that come into play in the ocean. And things like that is we need to be able to understand how they work and be able to model them to predict how the ocean circulation is. You see how this dense water that forms into the Antarctic margin cascades down to the abyss. Anyway, I can watch this all afternoon. It's pretty good animation. I think it took them quite a bit to do it. This is all from a model run in Australia. Right. All right, perhaps. And here we see these are these isopycnals that I was talking about. You see how they are slanted. That's another. Especially in the Southern Ocean, they are slanted like that. So, for example, these numbers mean things for something. I get confused. I mean, whatever, even it's 1037 or 1036, like this goes off my head, to tell you the truth. But, people like, this is part of the lingo of the oceanographers. Like, sometimes we talk with these numbers, okay? And sometimes because there are 1,000, we even forget the first 1,000 bit, and we talk about the 36 isopycnal or whatever, something like that. Anyway, I'll go on. So now, if you have any questions, fire me up. Huh?
So why the isopycnal lines are slanted? I didn't get that.
Well, it's because of geostrophic balance. We can. What? All right. So let's see. Let's see if some of these right. Yeah, you have new ones? Oh, all right. Okay. So you would expect that if you have something like that, this is unstable. If you do this in your bathtub, if you put this is your bathtub, and you put warm water here, cold water here, like that, what will happen in 1 millisecond? It will slide over, and it will be waves at the top, and and then everything will be like that, right? This will be the equilibrium. Okay, other way to see it is because I don't know, there will be a pressure gradient here. I think I may be drawing it wrong, but the pressure gradient will be towards this direction. So that's why you will say, well, this can never be balanced. But because the Earth rotates, there's also the Coriolis force. So if with this comes a horizontal flow like that, like a current, then this flow here will also be experiencing a Coriolis force in this direction. I hope I'm doing the signs right and whatnot, but it's something like that. So this will be the pressure gradient force. I may have used, I may be in the northern hemisphere now, okay, but something like that. So this will be the pressure gradient, and this will be the Coriolis force. And one will balance the other, and you could have an equilibrium state that looks like that. And in the Southern Ocean, this is the Antarctic circumpolar current. There is a very strong current that is like that. So that's why the isopycnals are slanted like that. But in your bathtub, you can never have something that will feel the Earth's rotation in just like a few meters or a few kilometers. So that's why you need to go to big scales to start seeing phenomena like that. Yeah. Right. Okay. So what I wanted to chat a little bit now is some of the challenges in understanding and modeling these things. Okay. So first of all, what drives the ocean circulation? That's another big difference. Perhaps that could have been in the different slide. So mostly winds, all right? Okay, so this is kind of like, there are people who will, get really heated up and chat about this and discuss that, oh, it's not like that. But anyway, but the consensus over the whole Earth is that mostly winds drive the ocean circulation and tides. Okay, so winds and tides are the main, you can't forget everything else to first extent. There are people who are talking about waves, whales moving around, and they're mixing the ocean and they're causing all. I mean, yes, that could be part of, this 1%. Even this 1% is an exaggeration. Okay. So how the winds? These are the winds at the surface of the ocean. You see, there's like strong eastward winds in the Southern Ocean. That's mainly what's driving the the current that goes around Antarctica. But it's a little bit intuitive. If you have wind blowing at the surface of the ocean, then the top layer of the ocean will start moving in that direction. Okay, that's momentum will be transferred from the atmosphere to the ocean. Okay, then we'll start having more other effects come into play, Coriolis force and whatnot. But that's like a main thing, how momentum is imparted into the ocean from winds at the surface of the ocean. So I don't want to talk too much about that. But I want to talk a little bit about tides. So we know what tides is. You go to the coast, you see tide comes in, tide comes out, and the moon and where the moon is attracts the whole ocean a little bit. So then the whole ocean moves a little bit with the moon in and out. Okay, that's what we call barotropic tide. The whole depth of the ocean moves around. Now, that's not what I mean when I say tides, but when this happens, because the whole ocean is forced to move over a complex bathymetry at the bottom of the ocean, there's mountains at the bottom of the ocean, as you probably expect. So then what happens? Imagine this, look at this a simple case here. Where is my mouse? I want to start it again. What happened? Everything froze. All right. Damn it. Anyway, it will happen. It will revive. My whole computer froze. But anyway. No, I'm looking at the movie here, but I can restart it. And while I'm restarting it, I can explain you what I mean, and we'll see the movie again. It's not even doing the restarting bit. Yeah, you see, this code is not for this laptop. Yeah. Ah. All right, it's doing the restarting bit. Now, as I was saying, if you force the whole water column to move over a little bump at the bottom of the ocean, then all sorts of complicated motions arise. Like, I don't know if you remember that video that was there, that, you know, these lines were lines of constant density, and then because they were forced to go left and right as if, that's what the tides, the barotropic tide, as we call it, or the moon tide does, moves the ocean in and out. But because the whole ocean was forced to move left and right from this, on this mountain, then the structure of the surfaces of constant density was becoming wiggly and whatnot. And sorry, I'm not good at multitasking. I admit that. I'm really bad. So I'll do this, and then I'll talk. It's my computer started now, so we are good with that. But you know, now the whole thing, the Zoom wants to start is the whole thing.
Oh yeah.
Yeah.
But we're back up. The projector's back on.
Yeah. All right. Done. Everything is like it's going crazy. Okay. And now you see my mess.
I'm very distressed by your unread emails.
Yeah, well, there's a lot of that. There's a lot of things that you see that you shouldn't be seeing here. Okay, Clerk's Water Winter School. All right. Oh, it's there. Like it has forgotten everything else. All right, here we go. You see all these wiggles come about because the barotropic tide forces all this ocean to move left and right about a small bump. And then you see all these wiggles that come about of that. That's what I mean mostly with tides. And to get a sense of how much this affects the whole motion, I'll show you here a movie. What they did here is quite nice. They took an ocean and they turned everything off. No ocean currents, nothing. It's just a quiescent ocean. It starts from rest, and the only thing it's on is the tides from the moon. And then, because then this forces the ocean to move left and right over all the mountains of the ocean, you start seeing, well, initially there's nothing, then you see, you know, a whole sort of movements everywhere. And if you notice, then if you know where this movement, if you can really see Hawaii here, Tahiti here, the mid-ocean ridge, because these movements emanate from where there is bathymetry at the bottom of the ocean. Okay, these are really fine scale things, and they vary with time scales of hours. I mean, the tide varies with time scale of, it has a period of 11 hours something. But you see this continuum of movements, it's one of the components of the ocean circulation. And this is another part of the complication. Now, how much time do we have? I'm getting injury time, yeah. We have 15 minutes.
We can go probably 20 minutes.
Yeah. All right. I'll talk to you a little bit about what all these eddies do, how they mix, or how they affect the circulation, and a little bit about the parametrization that is very common in ocean models. Perhaps you've heard it before. It's the mesoscale parametrization or the Gent-McWilliams parametrization. We don't need that in the atmosphere because in the atmosphere the mesoscale eddies are much bigger, so we have the adequate resolution to resolve them. But in the ocean, we are at the point that we still need them. So let's imagine the tracer dynamics, how heat or salt or everything evolves in an incompressible ocean. Okay, so this C here is the concentration of either heat or salt or your favorite tracer. Okay, and it's just advex and diffuses. Okay, but now let's imagine that we are like in a model world, and we know that we cannot have like a model with a grid spacing of 1 millimeter all around the globe. And I've shown you that there are some motions that occur at these like meter scales or sub-meter scales. What we have is a model that, you know, it resolves some things, and then the rest of these things are unresolved. The same for the flow, the same for all flow fields. Okay. So if you plug this back in, and if we have time, we could do it in the board, but you'll get this equation. Okay. So you'll get, oh, what nice, you get the same equation as the one you started with, but for the blue things. And then you get some leftover, which only involves the red things. Okay. I didn't do anything else other than rewriting and using the incompressibility here, and you'll get that. No approximation whatsoever. So you could be solving this or this. It's the same thing. The model actually solves this. It doesn't know about the red things. Okay, the red things are what we call subgrid fluxes. Like everything that is below your model's capacity. So if we had a model that had like 1 millimeter resolution, it would also solve for this, and all right, everything will be great. But usually we don't have this. So what we should do, because if we just ignore them, it will be wrong. Okay. So what we want to do is to somehow parametrize them. So somehow write this bit that we don't know as a function of the things that we know. Okay, that would be great. If we can do that, and that would be an equal sign, it's great. Then we plug it back in, and then we don't need the red things, right? But it's very hard. Like, how do you find this functional relationship? And sometimes it's not even possible. It's not possible to express these subgrid fluxes in terms of the things that you resolve. But a common idea is that all this turbulence, what does it do? It diffuses things. It steers things up. Okay, it makes things steer up more. So we can approximate it with what we say a downgraded eddy viscosity. We can approximate this flux that we don't know with the negative some coefficient here of the gradient of the tracer concentration that we know. And if we do that, this becomes like a diffusion, because then this term that was here, sorry, damn it. Here's where I should be looking. So this term here, minus the divergence of the flux, becomes kappa times the Laplacian. So this is like an extra viscosity, an extra diffusivity, sorry, in this case. Okay. So that's a good approximation. I mean, that it works more or less. Now, we can have something a bit more elaborate. We can have different diffusivities for the horizontal and different for the vertical. Remember, like, so if we have, instead of here, it's like having the same diffusivity for all directions of the gradient. You know, it multiplies also the ddx of c, ddy, and ddz. But then we can have a different, you know, instead of a constant here, we can have a matrix, and then the horizontal will be different than the vertical. Okay. So we expect, as I was telling you, that horizontal motions are more free and more easy to have rather than vertical motions. So they will steer and mix much more. So I would put here, like, you know, I don't know, 1,000, and here 1, or here like something that is much bigger in the vertical. Okay, if we are doing that, we are assuming that there's like different mixing happening in this direction compared to this direction. Okay. But that's not quite how it works. What we really want to do is to have something that is different in this direction, or 0 actually in this direction, and it's something in this direction. So we want to be able to write, instead of writing this matrix here, find a matrix which like goes at every point in the ocean, see how the isopycnals are, and arrange it so that there's no diffusivity across isopycnal, and there is a lot of diffusivity along isopycnals. Okay, so that's the idea, and that's what, that's what this. So if you can do that, and you can go at every point and compute, it's like just a rotation. Say how much do I need to rotate? So my vertical is in the direction normal to the isopycnals, and my horizontal is in the direction parallel to the isopycnals. That's a different direction in every space in the ocean, but you can do it, okay, if you know the isopycnals. So that's what we're doing. We do. And then there's like a little other, but assume that this bit is that, okay? Now, this is, people call this the Jen-McWilliams parameterization because Jen and McWilliams came up with it. Or they call it the isoneutral diffusion because you have diffusion in surfaces of neutral density. Okay, that's another way. And this is what all ocean models have. If you don't have this, you cannot run anything almost. Okay, if you don't have this, you have to have very, very high resolution to resolve all these mesoscale eddies. Okay, otherwise you get something that's completely wrong. Now, there's some problems with that because as we are here, everything is all good and nice. As we are below this is like this mixed layer that I was talking about. So in this mixed layer, we don't want to have this structure because here we have motions that move across isopycnals. So we want somehow, as we are going up, to turn off this parametrization and then let, I don't know, some other parametrization come in play. Or other problems could be, if we start increasing the resolution of the ocean and then we also have the parametrization, isn't it a little bit like double counting? Yes, it is. Or some mesoscale eddies are bigger closer to the tropics and they are smaller closer to the poles. So if we are in this intermediate resolution, we need to have this turned off in the tropics and turned on in the poles. Like there's all sorts of things like that, okay? But that's the best we can do, and that's what we're doing now. So let me show you how a model looks if you don't have this parameterization on, but you have a high enough resolution to resolve all these eddies. This is how the surface currents look like, and this is pretty close to reality. We know that it's close to reality because we have satellite observations also of the surface currents. So we know that this is pretty close to reality. If you have the parametrization on, don't be scared now. This is how the ocean looks like. All right, that's the best we can do. This is what IPCC reports use.